Let's prepare on roof trusses. So roof trusses. So roof trusses is nothing but it is the assembly of the steel columns, beams and everything only. So we have seen it already, no? So we are going to study some terms which is very important in this roof truss, okay? So the first thing I have drawn a simple roof truss here so that the angle at the edge, no? So it is your theta, which is your slope, and the length of the span, that is the span of the roof truss, and then the height, so you can call it as the rise of the roof truss also, okay? So based on this, the pitch value and slope value are calculated. So pitch is equal to h by l, where slope is equal to tan theta, which is h by l by 2. So it is nothing but 2h by l, so it is 2 times the pitch, okay? So these both are very important. If the pitch is less than 1 by 12 means we call the trusses the small, and if it is 1 by 12 to 1 by 5 means it is medium. When it is greater than 1 by 5 it is large. And the next important thing is spacing of the roof truss. So here it is 1 by 3rd to 1 by 5 of the span of the truss. So for economical spacing, the cost of the truss is equal to 2 times the cost of the purlin plus cost of the covering. Okay, so this is also very important. Purlin we have already seen, no, it's just a beam like thing we'll be using in a roof truss, and covering means the above sheet. We'll be covering the roof truss with any sheet, no, so that sheet is only called as covering here. And then the elements of the roof truss, okay? So here the roof truss is given like this. So this portion is called your principal rafter, okay? So this one, no, so this will be called your principal rafter. And then this horizontal structures, no, so these all is called as purlins. The purlins will be connected, or it will be joined by sag rods, okay? So these parts, no, the small parts are called as sag rods. So above this purlin only will be covering the sheet, okay? And then the rafter bracing. So rafter bracing is also very important because these are just for connecting the purlins together. So to interconnect the purlins, okay? So this will give you more strength for the purlin. So when we'll be using this is when there is heavy loads are placed, means we have to go for this rafter bracing, okay? And then the topmost line is called ridge and the bottommost line is called eave, okay? So these are the basic components to be studied here. So now this portion, so if you take this portion, how it will look means like this it will be looking, okay? So here this top portion is the covering, that is the sheet we are applying, no, so that one, then the purlin section, and then the principal rafter. So principal rafter will be the base for everything, okay? And after this, here and all we'll be providing column for the transferring of the loads, okay? So this purlin may be of any shape, it may be of I section, box section or anything, okay? So now we are going to study some basic design concepts here, because the complete design is not necessary because it takes more time. They can't ask that in the objective exams. So some basic important factors alone we'll be studying, okay? So the first thing we are going to study is the design loads. So it is categorized into 4 things: dead load, imposed load, then snow load, and then the wind load, okay? So the first basic is dead load. So here the roof covering will provide some load, and the weight of the purlins will give you some load, and then the self weight of the truss. So it is taken as 100 to 150 Newton per meter square on the plan area, okay? So based on the plan area, we'll be calculating the self weight of the truss. So all these 3 loads will give you the combination of dead load. And the next is the imposed load. Imposed load means it is live load only. So it is basically, if anything is not mentioned regarding the slope and if they are asking, means the basic value is 750 Newton per meter square or 0.75 kilonewton per meter square, okay? So based on the slope and based on the access to the roof truss, the values changes. So let us see that also. The first thing is for slope which is less than or equal to 10 degrees. So slope we have already seen, no, the angle of that rise and the horizontal, that is the span of that roof truss, okay? So if it is less than 10 degree and the access is provided, means it is 1500 Newton per meter square. If the access is not provided, means it is 750 Newton per meter square. And for slope greater than 10 degree, for roof membrane and sheets and purlins for if you're considering that alone means it should be 750 Newton per meter square minus 20 Newton per meter square for every increase in slope over 10 degree. Okay, so this is the condition. So this they will be asking, how they will be asking means they will be giving you the slope and they will be asking the live load to calculate. Okay, so for example, the slope of the roof truss is 30 degree. That means it is greater than 10. Okay, so we should go for this formula. So what we should do is it is 750 minus 20 into 20 because 30 minus 10 is 20 degree, no? So 20 times it has to be increased with, it has to be minused with 20. Okay, so it is 750 minus 20 into 20. So you will be getting 750 minus 400. So the answer will be 350 Newton per meter square. Okay, but see the next line, but minimum of 400 should be given. Okay, so if it is coming below that means also you should at least provide 400. So if this is the question that I asked, no, so if this is the question they asked means the answer should be not 350. Okay, it should be 400 Newton per meter square only. For member which is supporting the roof members purlins such as truss beam girder. So for these parts and all, when you're calculating the live load, it should be 2/3 of your dead load. So dead load we have already calculated, no? So we can simply take 2/3 of that load as the live load here. And the next is the snow load. So it is 25 Newton per meter square per 1 centimeter depth of snow. Okay. So in the tropical regions, if the snow is not there means the depth is 0. So automatically we can neglect this snow load. Okay. If the slope provided, in the areas where snow is there, the slope provided is greater than 50 degree means we no need to add this load to the design because it will itself slide down. Okay, so when the angle is greater than 50 degree. Okay, and then the wind load. So in wind load, the design wind velocity. So first we'll be calculating the velocity and then we'll be going for the pressure. Okay, so pressure is only your load we are considering. So here velocity is Vz is equal to K1, K2, K3 into Vb. So all these are factors. Okay, so let us see what are those. K1 is the probability or risk factor. K2 is the terrain height and structure size factor, and K3 is the topography factor. So all these factors will be in the code book. So based on the region we will be selecting that. Okay, and Vb is the wind speed at a height of 10 meter at the locality. So this is also based on the code book. So in code book, the regions will be separated. So based on the wind velocity, and for each region a value will be given for this Vb. Okay, so we'll be just substituting that value here. And then the design wind pressure is equal to 0.6 times this Vz square. So this will be your wind pressure. And then this wind pressure, no, so on whole it is divided into external wind pressure and internal wind pressure. Okay, so the external wind pressure is depends on the slope. Okay, so the outward wind that is hitting on the roof truss, no, so that based on that. And the internal wind pressure means it depends on the permeability of the structure, because based on the permeability the air will penetrate inside or it may be heated outside. Okay, so based on that these both values are given. Okay, so all these are based on the type of that material they are using as a covering also, it depends. So the first external wind pressure, now so it depends on slope. Slope means based on the angle, so it ranges from some 0 to 90 degree, and based on that angles the values are given. So that tabular column is not necessary because it's a huge tabular column and it's not necessary. If you want to know that means you can just refer the code book. The internal wind pressure is, it depends on the permeability of structure. So this is very simple. So they have asked this. So here if it is zero permeability, that is the type of the building is zero permeability, means the internal pressure can be taken as 0. Okay, if it is normal permeability up to 5% means it's 0.2 times the pressure, and medium opening 5 to 20% means it's 0.5 times the pressure, and large opening means it is 0.7 times the pressure. Okay, so this zero permeability means there will be no opening in that structure. Okay, and normal permeability means just like windows and doors will be provided, so through that the permeability of air will be going. Okay, and then the medium and large depends on the area, the wall area we are opening it for the air to travel. That's all about the roof truss design, loads and everything. So now we will see the design of the purlin. Okay, so here the purlin is designed as it's a beam, we know that, no? So this should be designed as a continuous or simply supported beam. Okay, so based on the IS 800, it recommends that it should be designed as a continuous beam subjected to biaxial bending. Okay, so biaxial, both the sides should be axially bending. So if this is the case, should be designed that purlin, then the purlin will be in a safe zone. Okay, so the moment, that is the maximum bending moment that a purlin has to be designed is, it is WL square by 10. Okay, so based on the major axis and minor axis, there will be two loads that is occurring in the purlin. So on major axis means we call it as the P, and minor axis means it will be H, the H load. Okay, so it will be differing in the directions, but for both the things the formula is PL square by 10 and HL square by 10 only. So we can generally study it as W with the load into L square by 10. And then the maximum deflection, so this is important. Here the maximum deflection is L by 180 for brittle cladding and L by 150 for elastic cladding. Okay, so this cladding we have seen already, it is just the covering which we are providing above the purlin, no? So that is only. If it is a brittle material, then that one, and elastic material means L by 150. So this L, no, so this is not the span of the roof truss. Okay, so this is all span of the purlin only. In all these formula, it's the span of the purlin only. Okay, and then in the right side, if you see me, here the diagram is given, no? So this is for an angle purlin. Okay, so as I told in the previous case with the I-shaped purlin, no, I section, here they have used two angles. Okay, so they have just connected like this, two angles, and the bolting is given here and everything. Okay, so that is only given here. So there is a condition for this angle purlin, that means the length of that angle section, no, so it should be L by 60. Okay, on that top side, that is the angle leg in the plane which is perpendicular to the roof covering. So this is the roof covering, and the perpendicular means it should be L by 45. When it is parallel to the roof covering, it is L by 60. Okay, so based on that, you can locate this L by 60 and L by 45. So it should be provided like this. Okay, so in this purlin also, the maximum bending moment is WL square by 10 only. Okay, so this is all enough for this roof truss, that is design loads, and the purlin design this loads and deflection. So this is all enough. So with this, the steel structures is over, and next we'll be starting with a new subject. Thank you and keep watching.